Hello, Spidey Physics viewers. I think I want to bring back the 7-minute summaries. Last couple videos with chapter 39, relativity and all that, I was trying to spend a bit more time reading the chapter, but man, I'll be honest with you, it takes a lot to record that, edit it, make sure I'm not saying any stupid shit or, sneezing or anything in that video. So I like the 7-minute summaries. I like them because I can film them pretty quickly and get some content out to you guys. But also, it's very useful to get immersed into this content that you're studying. You want to spend as much time as possible, and we have busy lives. It's good to just spend 7 minutes, like 7 minutes. Watch this video on 2 times speed, 3.5 minutes of a chapter summary. Obviously, the videos are going to be longer because I'm kind of yapping at the start and at the end. But we got a 7-minute video of the introduction to quantum physics, my personal favorite subject in physics. I'm not going to say I understand it completely. I don't think a single person understands it. Freaking, what's his name? Richard Feynman quote of the century. No one understands quantum mechanics. But right now we're going to get introduced to it. So let's take a look. Chapter 40, we got a couple sections here. Section 1, black body radiation and Planck's hypothesis, the photoelectric effect, the Compton effect, the nature of electromagnetic waves, wave properties of particles, a new model, the quantum particle, the double slit experiment revisited, let's go baby, optics, the uncertainty principle. 8 sections. I'm not sure how many pages there is. You know what? We're just going to get started. Let me set a timer for 7 minutes.
All right, 7 minutes. Starting now.
Okay, 7 minutes goes quick, so I'm going to have to go quick. In chapter 39, we discussed that Newtonian mechanics must be replaced by Einstein's special theory of relativity. When dealing with particle speeds comparable to the speed of light. As the 20th century progressed, many experimental and theoretical problems were resolved by the special theory of relativity. For many other problems, however, neither relativity nor classical mechanics could provide a theoretical answer. Attempts to apply the laws of classical physics to explain the behavior of matter at the atomic scale were consistently unsuccessful. Okay, crazy. Let's read sentences at the start of paragraphs. Let's look at pictures. Let's read some little images and pitfall preventions. Expect to be challenged. If the discussion of quantum physics in this and subsequent chapters seems strange and confusing to you, it's because your whole life experience has taken place in the macroscopic world where quantum effects are not evident. All right, thank you. Pitfall prevention number 1. Black body radiation, section 1, and Planck's hypothesis. Let me check out some of these bold words. Thermal radiation, okay, from classical viewpoint. Thermal radiation originates from accelerated charged particles in the atom near the surface of the object. Let's read this over here. The opening to a cavity inside a hollow object is a good approximation of a black body. The whole acts as a perfect absorber. Okay, then we have black body radiation and the word black body over here in bold. And the whole section is called black body radiation and Planck's hypothesis. So black body is something, I guess, a new word that we're introduced to. Not sure what it means. I'm going to note down that black body is bolded out many times here, and then later I can Google search what does the black body radiation law mean, Stefan's law, okay, we have a first equation here. P equals a bunch of interesting symbols. It says the total power of emitted radiation increases with temperature. Let me check the timer. 4 minutes, 55 seconds. I do go pretty slow at the start and kind of end off really fast. So let's read these bold things here. The peak of wavelength distribution shifts to shorter wavelengths as the temperature increases. Okay, let's take a look at this graph. We got wavelength on the x-axis and intensity on the y-axis. And we have a couple interesting curves here, and they show you this 4,000 K, 3,000, 2,000 K. K, I think, refers to the temperature in units of Kelvin, not Celsius, not Fahrenheit, not anything else. Kelvin is normally the physics unit used. Interesting graph. I'm going to keep a mental picture of this graph because I think it might be important to this section. And it says Wien's displacement law. Wien's. Okay. We got something else here. Rayleigh-Jeans law. I remember the name Rayleigh in the optics section, but I'm not going to spend too much time on that. Looks like we have a similar graph to the one I saw on the previous page. The classical theory red-brown curve shows intensity growing without bound for short wavelengths, unlike the experimental data, the blue curve. Okay. Oh, we got a picture of Mr. Max Planck. This guy is normally credited with the introduction of, or like the beginning of quantum physics. Let's read over here. Planck introduced the concept of quantum action, Planck's constant H, in an attempt to explain the spectral distribution of blackbody radiation, okay, which laid the foundations of quantum theory. Let's go. 1918, he was awarded the Nobel Prize in Physics for his discovery of the quantized nature of energy. That on its own is insane. If we are interested in quantum physics, we could take a look at Max Planck, search up Wikipedia, what's his history, what did he do, what happened after, he talked about his Planck's constant. You're going to get a lot of introduction to the field. But let's take a look at the timer. We got 3 minutes, bro, and I'm still in the first section, so we're going to have to zoom through. Interesting graph over here. It says allowed energy levels for an oscillator with frequency F. Okay. Similar kind of graph as we saw before. An interesting function over here looks pretty crazy with I as a function of lambda and T. Intensity as a function of wavelength and temperature, perhaps. Planck's constant. We saw this at the beginning of the optics section, and here it is introduced. I don't have too much time to look at it here. We got an example. Of course, fantastic thing to go through these examples, put into practice some of the equations that are introduced. Second section. Damn, I really spent the entire, we have 2 minutes, 20 seconds. The photoelectric effect, photoelectrons. We have a graph. We have kinetic and potential energy. The sum of them equals 0. That looks pretty cool. We have a couple of points here. I'm not sure what these points are, but I can't read through them. Just going to keep in mind that those points are probably important. We got a table here, work functions of selected metals. Interesting. And then we have photoelectric effect equation. This is a very cool equation. I think this was proposed by Einstein. Very simple equation. It's literally a straight line. Here we have the y-intercept. Here we have the slope as a function of frequency, I believe. And here we have the y value. Here they are actually plotted for different metals. Cutoff wavelength. All right. Sorry, guys. I'm going to zoom through here a couple examples. And 40.3 with 1 minute 20 seconds, the Compton effect. Oh my goodness, I cannot go through all this. Compton shift equation, derivation of the Compton shift equation. A couple more examples. The nature of electromagnetic waves. This is literally 2-3 paragraphs and nothing else. Okay. Looks pretty cool. The nature of electromagnetic waves kind of sparks some kind of curiosity in me, so maybe I'll go back and read it. The wave properties of particles. And we have Louis de Broglie, also a very crazy guy. He introduced this thing, which was a very important thing for quantum mechanics. We have a couple of outlined equations. The Davison-Germer experiment. Okay. A couple examples. The electron microscope. Damn, a lot of subsections here. A new model, the quantum particle, with 30 seconds left. Oh my god, wow, that is a lot of equations. Okay, phase, speed of wave in a wave packet. Okay, what the heck? The double slit experiment revisited. Okay, this looks familiar. Pretty short section. The uncertainty principle, all in yellow. We got Werner Heisenberg, pitfall prevention. And we're done. Let me check the timer. We got 10 seconds left. I'm gonna stop the timer so it doesn't interrupt the video. But that was rough. That was rough. As you guys remember with my previous videos, we got the summary here. Let's take a look very quickly at the summary. So black body radiation in the first box. That is something to note down. And we have an interesting equation over here. Energy of a packet is frequency, and then H is the Planck constant. Then we have another concept we learned about very quickly, or we saw. Photoelectric effect. We saw the word work function. We saw this equation here, which I told you guys was a straight line. There's the word photon over there, bolded. We got the Compton effect as well. I really zoomed through that section. Kind of an interesting and scary looking equation here. Whatever, let's keep going. Light has a dual nature in that it has both wave and particle characteristics. Some experiments can be explained either better or solely by the particle model, whereas others can be explained either better or solely by the wave model. Interesting sentence. And I'm sure that was included somewhere in the chapter. I just zoomed through it, 7-minute summary. I don't read like barely any words. I just kind of look at some pictures and stuff. But a very interesting sentence. Maybe I can plug this into ChatGPT and be like, explain this to me. What does this mean? I have no clue what this means and I'm interested in it. Good way of studying. Every object has a mass m and a momentum p equals mu. Um, this has wave properties. The de Broglie wavelength is given by this equation. I remember de Broglie. I've heard that guy's name quite a few times. So interesting to search up the history of de Broglie. What did he do? You know, what are his theories, whatever. By combining a large number of waves, a single region of constructive interference called a wave packet can be created. The wave packet carries the characteristic of localization like a particle does, but it has wave properties because it is built from waves. For an individual wave in the wave packet, the phase speed is blank. For the wave packet as a whole, the group speed is blank, okay? For a wave packet representing a particle, the group speed can be shown to be the same as the speed of the particle. Okay, this is a crazy sentence, and it actually goes along with this dual nature. They're basically saying, okay, we learned about the double slit experiment in the optics section where we defined waves like light waves as either rays with the ray approximation, and then later when we actually looked at the double slit experiment, we modeled them as waves, like actual waves, not rays. And then we saw that light, I guess, is composed of a photon, but at the same time you could look at it as a wave. So in this little section here, they talk about how light specifically has this dual nature. And over here in this little box, that they tell you how a photon, which can create constructive interference, can be called a wave packet, which has properties of waves. So they're trying to create some kind of mathematics here that can explain an object that is actually an object, like a particle, and at the same time a wave, right? Because a wave and an object are completely different. If you look at a cup on a table, you will say that is an object. That's not a wave. And if you look at a wave in an ocean, you'll be like, that is a wave. It's not an object. I mean, you can, I guess, identify that wave as an object made of water, but there's some differences, right? So they're trying to kind of break apart those differences and explain them mathematically. And the weird thing is, in quantum mechanics, things behave both as particles and or waves. In different scenarios, maybe they're one at the same time. I have no clue, guys. We're going to keep reading. Every object has a mass. Oh, I already read that. The Heisenberg uncertainty principle, kind of one of the last things we read. And we have a couple of equations over here. All right, so that completes my 7-minute summary. I know it was kind of a crazy summary, but we can zoom out over here. Let's go to all pages. Hold up, let me go to boom, and then let me go to all pages. Damn, I'm gonna have to go all the way here. I just want to see how many pages this whole chapter is. Maybe it'll be kind of interesting. Okay, so here is the start of the chapter. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 pages, and the 26th one being the summary. So 26 pages. As you saw, it was insane going through them in 7 minutes. You got to go through like 2 pages per second. And overall, looking at this stuff, you kind of just want to solidify in your brain a couple of key concepts. And those key concepts, you can actually see them in this section here. So all of the bold words: blackbody radiation, photoelectric effect, work function, Compton effect, dual nature of light, de Broglie wavelength, wave packet, phase, speed, Heisenberg uncertainty principle. Write all those down on a piece of paper. Try to define them, try to explain what they are talking about, and that's a good way of practicing and studying for a test. Then when you feel comfortable with that, go into some problems. You saw a bunch of examples through this 7-minute summary. Feel free to ask some questions in this YouTube video, drop some comments down below, and I'll see you guys with the next video. Thank you again, as always, for watching. I love y'all. Peace.